Let's do it.
We're going to be doing a little TIG welding today on some cold roll steel in a aerospace test welding fixture made by A-Bomb 79. Aerospace metals like 17-7 stainless and Inconel 718 are super expensive, so it makes sense just to get some practice on plain, cheap, cold rolled steel. And while I'm welding this, I'm also going to be experimenting a little bit with high-speed pulse versus no pulse. This is a CK Worldwide MT200. It goes up to 200 pulses a second. And I will set the background amps to around 40%. A little bit later in the video, I will compare a joint using no pulse at all and see if we can see the difference. To get purge gas to the back side of the joint, I'm using a dual flow meter. You could also use two separate cylinders with single flow meters, but the dual flow meter is an easy way to do it. I'm just using regular old automotive vacuum line for the purge hose. That's fine for cold rolled steel. You might need something better for titanium and exotic alloys. If you ever have to take a test like this, you want to be careful not to use too much purge flow on the fixture. That'll blow your torch gas away. I'm using a 045 ER80 SD2 filler because the thickness of the base metal is less than 040. You can see that I have just a little whisper of a gap there. The gap is totally not necessary. You're going to get penetration pretty much, but the gap helps a little bit in distortion. So I got a nice low startup. This machine has a 5 amp startup, very helpful for aerospace type work like this. Let me show you that tack again here. One more time we'll go over that. I add a little bit of extra metal on my end tacks, and I'll explain why here in a minute. First thing you want to do is puddle both corners. Don't give it much amperage until you get them to join. Kind of stab the rod in there, get them joined, then they'll conduct heat evenly, and you can add a few extra dabs, and it'll give you a little bit of fudge factor when you're welding from or welding to. It'll keep you from melting those ends away. The aerospace welding specification allows for some melting ends away, but when I used to administer this test, I didn't allow that because all of our parts had ends that we didn't want to melt away. I was probably lenient in other areas that I didn't feel were as important, but melting ends away is something I felt like was super important. So the way we administered this test was to start in the middle and weld to one end. That way we could require a stop and a taper off and a crater out taper off in the middle to demonstrate the ability to not leave a crater crack, which that's another thing I felt was super important on aircraft parts. Welding to that tack where I added a few extra little dabs. I'll show you that right now. Right there I start to taper off. You can see I did not even come close to blowing the end away because I had a little extra heat sink there, a little extra dam there of extra mass, of extra metal with that extra few dabs on that tack. Here it is in slow motion. As soon as I get right about here, I start backing off the pedal, taper off and back up the arc a little bit, and it doesn't leave a crater crack or a mark or a crater hole or anything like that, and keeps the end intact. And the objective here is, if this was an aircraft part, if it was a crack and you were welding out to the end, you'd want to be able to have metal there that you could grind off and then maintain your dimension. You don't want to blow the end away. All right, once that's welded, now we start on the other end and we weld to the previous weld and then taper off when we get there so that we don't leave a crater crack there. You see how that extra little bit of metal kept me from melting that end away there? Even though I set the amperage to about 100, this is showing the average readout here for the actual welding, and I'm not quite full pedal. This is real time. This is the speed that I'm traveling. I'm trying to keep that hot tip of that rod shielded with the argon coming out of that cup. Trying to maintain a nice tight arc length. You can see the Jazzy 10 is doing a really good job of shielding a really big argon envelope there. That's always helpful on aerospace tests. Here I'm coming up on the previous weld, so I slow down a little bit, add a little bit less filler, keep traveling, taper off the amperage, and kind of teardrop it out. Now I know that not everybody watching this is facing an aerospace welding test, but this is just good fundamental principles for basically any kind of sheet metal welding. If you're tying into a previous weld, that's a good way to do it. Now the reason I required that taper off thing in the middle of the test joint is because that's the most likely place for a crack, especially on crack-sensitive alloys. Let's take a close-up look at that. And now let's take an even closer look with some magnification, and let's zoom in a little bit. That's where you're likely to have a crack right there. And it happens a lot on chromoly, on 17-7 stainless, on Inconel. But if you keep traveling as you taper off while adding less and less filler, you can avoid that crater crack. I'm turning the pulse off now, and I'm just going to weld it with straight current. About the same amperage output though. There's slight differences. 200 pulses a second is a lot. And what it does, it stiffens the arc up, but it's almost like welding without pulse. There's some really subtle differences. In a lot of cases, I would prefer to do this type joint with no pulse at all, but you know, the machine's got it, and so I like to experiment. That's how we learn. All right, let's do that other half now, just like we did before. We're going to come up on that previous weld. Just the same old fundamentals. We're trying to keep a tight arc, move along at a consistent rate, keep the hot tip of the filler shielded by the argon. And as we move into that previous weld, quit adding filler, keep moving forward, taper off the amperage to 0, and that's what prevents a crater crack, especially on crack-sensitive alloys like chromoly, precipitation hardening, stainless, Inconel 718, etc. There's the no pulse, there's the 200 pulses a second. Definitely a little bit of difference, not like night and day. Now for this video, I used 332 electrodes. 1/16 would have been better, but as long as you sharpen them like a needle, like this, you can almost do the same thing as you can with the 1/16 electrode. So I'm going to run a bead on the edge of this 038 material with the electrode sharpened, really sharp, really long taper. That's what I would do. This is really good practice for an aerospace test. To be able to run a bead along the edge of something about this thickness, that's the kind of heat control you need to practice for aerospace welding. The great thing about it is that you can just grab some cold rolled steel, sheet metal like I have here, and use an Inconel filler rod or a Hastelloy filler rod and work your way down to as thin as you can do and do edge build up like this. And that's some of the best practice you can get for practicing for an aerospace welding test. All right, let's get into the process now. One of the most important things is filing an edge on a joint like this. It's best to use a clean new file, followed by a acetone wipe. Sometimes you might use a fine abrasive to knock down an oxide layer, depends on the alloy. This is just 304L stainless, doesn't really require anything other than a filing and a wiping. It would be rare to weld this alloy for a test. Mostly it would be something like 321, 17-7. 10 CFH on the fixture, and I will use some small pieces of tape to tape off the unused portion of the argon trough. This is a nice WeldTech SW 320 amp water-cooled torch I'll be using, and on that number 12 cup I'll be using about 25 CFH. This stands quite a ways up off the table because it's pretty thick, so I'm using this little block that I made a while back to get comfortable with. That's what I'll do for this stainless joint. Filler wire, even though it looks clean, it's usually not. There's usually some residue from wire drawing lubricants and things like that. Now that I've cleaned the wire, I'm ready to tack the ends. I'm adding a little extra wire on each tack. A couple of extra dabs. I like heavy tacks when I tack on the very end like that. It gives me some, like a launching pad to prevent from melting away when I travel from, and it also gives me a little extra second when I get to a heavy tack on the very end when things are kind of heated up. So you don't even have to tack a joint like this. The fixture will hold it down pretty well, especially if you really lock it down. The reason I gapped it, two reasons. Number one, it helps it distort less. And even though I gapped it about, say, 040 or so, it pulled shut to where it's less than 030 now, and it just really helps me see the line. It's not at all necessary to have a gap to get full penetration on something this thin. But sometimes it just depends on the alloy. Sometimes a gap helps. Sometimes it hurts. 51 amps it takes to penetrate this stuff. That was what I settled in at. It would probably take a little bit less than that if it wasn't such a chill block. Anytime you put something in a fixture that's a heat sink or a chill block like this, it's going to take a few more amps to weld than it would be out in its free state. But you have to have something to hold it down and keep it straight, and a fixture like this is very common in the industry. Let's take another quick look at that tapering off there. Again, this is why I put a little bit heavier tack on the ends, and I'll show the other end in a minute, but once I get about right here, I start letting off the foot pedal a little bit. Then I keep a really close eye on the leading edge of that puddle, and when I watch it run about halfway into that tack, then I really get off on the foot pedal and then back up the arc a little bit as I taper off slowly. And that works really well for not only a test like this, but it works for actual aircraft parts when you're welding a crack out to the edge of something like that, and then you have to maybe blend it off flush afterwards. It's just really a good technique. Now, something I didn't mention, there's a reason why I'm welding this in halves, and it's called backstep welding when I weld to a previous weld. And that basically is because this is what I required when I had to administer these tests. I thought it was a pretty bad idea not to have any stops and starts, so this at least demonstrates the ability to taper off and not leave a crater crack or a crater eye on some of these crack sensitive alloys. So you can see there in slow motion, it works just as well coming from a tack as it does tying into a tack. And then when I tie into the previous weld here, I just keep the torch moving, add less and less filler, and kind of comet trail on out. And that wound up being about the best technique I could find for crack sensitive alloys like Inconel 718, 4130 chromoly, or 15-7 pH stainless. Let's look at it backside now and see if the fixture did its job, see what the purge looks like. It looks pretty good. It looks like we can tweak it a little bit with the flow rate and maybe the amount of tape I put on there and maybe some other things and get it even better on the backside. A 2G horizontal test is really not that much more difficult than in the flat position, but in my experience they're more likely to fail X-ray. Oftentimes you're going to be using a fixture like this for aerospace tests, and they have a little narrow argon trough. It doesn't require much argon. In this case, 5 to 10 CFH is plenty. You've kind of got to do a little testing, maybe lick the back of your finger and see if it's too much flow. If you use too much flow, it'll fight against your torch gas. I'm using a number 10 cup here, 20 to 25 CFH with the Jazzy 10 cup. I'm going to get tacks on both ends, and I often put just a little extra metal on my tacks, just an extra dab or two. It gives me a little extra forgiveness when I'm welding from or going to a tack to prevent blowing the end away. Once I've got the tacks on it, I set the fixture up in the 2G position, and here's a really important tip. You want to angle the torch, angle the tungsten upward. For a horizontal weld, you don't want to have it straight in or even never pointing down, but pointing upward like this will help the argon reach the joint, and for some reason it just helps pass X-rays. Now I did a little experimenting here. I'm going to go full pedal with 48 amps on this machine, and that gave me a 46 amp readout. So I went full pedal. You need a little bit less amperage for stainless steel than you do carbon steel. Also, a good tip is to use one size lower in the filler metal diameter. So in this case, I'm using an 045 filler metal. Base metal is 063. 045 seems just about right. I'm going to come up on the very end here in just a second, and you'll see why those little extra button tacks come into play. I'll show this in slow motion in a minute. See, it gives me a little extra second to back off and not blow the end away. Now the D17 spec gives a lot of leeway in blowing ends away, which I really don't understand that. It's never a good idea to blow an end away. So I'm going to show this in slow motion here. This is half speed. I'm coming up on that end tack. I'm kind of like really eyeballing the left side of that puddle and slowing down, tapering off, letting it soak for a second, and then tapering off the amperage. And I know I'm going to get 100% penetration all the way end to end, and I'm not going to blow the end away by doing that. The reason I started in the middle and welded to the end, and now I'm starting on the end and going to weld to the middle, is this is how I used to require tests to be done when I was administering this test myself. We did an awful lot of backstep welding, and that's what this is when you're welding into a previous weld. We did an awful lot of it on parts to prevent distortion. One of the main skills in taking any test should be to not leave a crater crack when you have to terminate a weld. So this is the way we did the test. We required starting in the middle and then welding into the middle and tapering off without leaving any kind of crater crack or any kind of problem that would show up in X-ray. Oftentimes in aerospace repairs, you're never welding more than a couple of inches anyway. Now, I used a 332 electrode here, and I got it kind of sharpened to a needle a little bit. I easily could have used a 1/16. Would have probably been a better choice for a joint like this. But a 332 did fine. It's well within the range. As long as you get a good sharp tip on it, you're going to get a good crisp start. Let's pull it out of the fixture now and do a little quick examination, see if we got full penetration, see what's up. In this video, we're going to take a look at some tips for passing a 3G TIG test. A few tips for how to prop, how to slide, how to glide, different ways to hold the torch. And of course, some good arc shots on how to tie in to the end tack. Just for this demo joint, I'm just using 304L stainless. That would be rare to do in aerospace testing, but it's just a practice joint. I'm going to be using purge gas on the fixture, so I need a dual flow meter here to make that work. When I make my weld tacks, I put just a little bit of extra metal on them. I have a slight gap in this joint, 0.40. By the time I get finished tacking, it's going to be more like 20 or 30 thousandths. And then when I start welding, that's even going to close up. Stainless draws a lot. I gapped it just mainly to help me see. I find that it helps also with a little less distortion when you're done if you have a little area for the weld metal to shrink. Totally not necessary to have a gap in this thickness to get full penetration. Notice that I'm reading out 46 amps here and I'm welding 063 material. I've found that with stainless you need about 2/3 of an amp per 1,000ths of thickness for a butt joint like this, especially if you have any gap at all. That 1 amp per 1,000ths rule is a guideline. Works on carbon steel and some other alloys, but a little bit less for stainless, a little bit more for aluminum. Here's a nice instructive arc shot right here, welding into that tack on the very end of the joint. Now we're going to take a look at that at half speed here in just a second, because I think there's something to be learned here. This applies to welding to the end of practically anything, not just a 3G test. We'll slow it down and blow it up a little bit. So this is half speed. I'm almost there. I'm keeping a real close eye on the front edge of the puddle. And right now it's joined into that tack. And so now heat is going to conduct a lot more evenly. And there it goes. It wicks right on up into the tack. And I start backing off the pedal and backing up a little bit. And that works for me when I'm welding on an end, pretty much anything. So now I'm going to weld from the bottom into that previous weld. And this is just a little bit different technique, but I'm still going to taper off amperage as I blend the weld into that previous weld. This is called backstep welding. It's used a lot in sheet metal welding and in aerospace welding because distortion needs to be limited, and backstep welding can really help in limiting distortion. Here I've magnified it just a little bit, and I'm coming in on the previous weld, and this is where I kind of slow down a little bit, let things melt together, let things blend in, and then keep traveling while I taper off and kind of teardrop or comet trail off. And that has worked for me really well, especially on crack sensitive alloys. So we're going to take a look at that at half speed now. I'm almost there tying in. Now I'm slowing down a little bit, make sure it has time to fully blend and penetrate, and then I add a little less filler until I'm not adding any more as I keep traveling and slowly letting off the foot pedal, and I taper it down into a little teardrop of nothing. Continuing to travel while I let off gradually the foot pedal is the secret there. All right, let's take a look at some ways to hold the torches. You saw me holding it another way, and that was mainly to get out of the way of the camera. I'm using a TIG finger here to glide along that fixture chill bar there. It kind of glides a little smoother than your glove can. It's not so much that you need any heat protection here unless you really have welded 100 joints and have really got that fixture hot. But it just helps you slide and glide along a lot smoother. So this is just an example of a previous video I did. I just really wanted to show how to hold the torch, and I didn't have time to film that footage on the stainless video. So this is just the aluminum joint on how I held the torch, and the same thing would apply to stainless. So let's get back to the stainless topic. Okay, let's pull it out of the fixture, kind of check the backside, see how we did on penetration. Now I'm noticing I got one little spot that discolored more than the rest of it. I think that was because the plates that I used for shim plates were kind of bowed a little bit. See that little spot? That should be white. So I either need to adjust my argon flow on the fixture or possibly just get a better mate on the chill bars. I'm pretty sure it was just the chill bars actually.